Okay, let's get started with today's class, right? So we are looking at root locus. So today I'm just going to complete a few more concepts related to the root locus, and then we'll move on with other topics from tomorrow, right? So, so if you recall, what we considered in the root locus, just to recap what we were doing, if we consider the basic block diagram, which has been our focus. So, G of s being the forward path transfer function, H of s being the feedback path transfer function, and let us say we have negative feedback, right. So, we were looking at what happens when we have one parameter in the open loop transfer function being varied, right. So, the closed loop transfer function was G of s divided by 1 plus G of s H of s, and the closed loop characteristic equation was 1 plus G of s H of s equals 0, right. This was with negative feedback. So, consequently what we looked at was what happens to the roots of this equation, right. So, as we vary a parameter, and what we did was that we considered the open loop transfer function G of s H of s to be some k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn, right. Of course, first we considered k to be greater than 0, right. So, that is what we have looked at, right. Now, the question that we are going to ask ourselves today to begin with is what happens in the case of positive feedback. Suppose let us say we had positive feedback with everything else remaining the same, okay. The structure of G of s H of s being k times s plus z1 to s plus zm divided by s plus p1 times s plus pn, right, and k being positive, right. So, if we had the same structure, and the only difference being the fact that instead of negative feedback we had positive feedback. So, how is this block diagram going to change? So, everything else remains the same other than the fact that at the summing junction I am going to essentially sum the two signals, right, rather than subtracting them as we did before. Okay. So, let us say due to some reason we had a structure like this, right. So, this was our W of s, right. So, that was our signal W of s. So, let us say we had such a case, right, positive feedback. Then what happens to these steps involved in the construction of the root locus, right. So, let us answer that question and let us do an example today. So, in this case the closed loop transfer function becomes G of s divided by 1 minus G of s H of s, right. So, this will be the closed loop transfer function. So, consequently the closed loop characteristic polynomial and the closed loop characteristic equation would be 1 minus G of s H of s equals 0, right. So, this would be the closed loop characteristic equation in this case. So, any value of s that satisfies 1 minus G of s H of s equals 0 would now be a closed loop pole. So, this implies that what happens as a result? This implies that any value of s which makes the open loop transfer function to be equal to 1 will be a closed loop pole, right. So, what will this give us? This will once again give us two conditions, the magnitude condition being the magnitude of G of s H of s being equal to 1, the magnitude remains the same, right, but the main difference is in the phase. Now, we see that plus 1 is on the positive real axis, right. So, the phase of g of s h of s is going to be an even multiple of pi, 0 included in it, right. So, one can say it is 0 degrees or 360 degrees or 720 degrees and so on, right, depends on how we count it, right. So, now rather than an odd multiple of pi, the angle condition is going to become an even multiple of pi, okay. So, that is what is going to happen, right. So, that is the main change that comes about when we have negative feedback, right. So, still like we are considering g of s h of s to be of the form k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn, of course k being positive, right. So, that is the condition, that is a scenario we are still considering, okay, even in the case of positive feedback, okay. Now, the question arises as to how the steps involved in the construction of the root locus change, right, with this modification, okay. So, that is what we are going to learn now, and we will repeat the same example once again to understand how the root locus in fact changes, right, once we change the nature of feedback from negative feedback to positive feedback, okay. Is it clear? Okay, what is the change that occurred? So, let us go to the document where I had listed the steps involved in the construction of root locus and figure out what really happens, right. So, it is pretty straightforward to figure out that since the angle condition changed, whatever steps that we learnt previously that were involved in the construction of the root locus and those that use the angle condition are going to change, right. So, let us go through each step. So, the first step was to locate the open loop zeros and open loop poles in the complex plane, right, that pretty much remains the same, right. So, because it does not matter whether it is negative feedback or positive feedback, this step remains the same, right. You locate the open loop poles and open loop zeros in the complex plane. As k tends to 0, we are going to have the root locus starting from an open loop pole, and they go to the m open loop zeros as k tends to infinity and along asymptotes if n is greater than m, right. So, that step remains the same. Now, locating the root locus portion of the root loci that lie on the real axis, obviously this step is going to change, right, because if you recall how we constructed this step, it depended on the angle condition, right. So, previously in order to get an odd multiple of pi, right, we looked at a test point on the real axis and then we looked to the right of the test point, right, and we argued that if the number of open loop poles and open loop zeros on the real axis to the right of the test point is odd, then we get an odd multiple of pi because each would contribute pi, right, and then that test point lied on the root locus. Now, we need an even multiple of pi. So, what do you think will happen here? Now, you take a test point, you look to the right, the number of real open loop poles and real open loop zeros to the right of it should be even, right, or it can be 0 because even we can have 0 degrees satisfying the angle condition, right. So, consequently step 2, I have typed the corresponding changes in the same document if you scroll down to page number 2. So, with with positive feedback, you see that step 2 is now changed, right. So, you see that the main change that comes about is the fact that the criteria is changed from odd to even, okay. So, you take a test point on the real axis and then you count the number of real open loop poles and real open loop zeros to the right of it, it should be even or 0, right. So, then that test point lies on the root locus, okay. That is how the second step changes, right. Now, let us go to the third step. Third step is to determine the asymptotes. Obviously, the asymptotes angle depends on the angle condition, right. So, what was the angle of asymptotes? Plus or minus 180 times 2k plus 1 divided by n minus m. That now changes to plus or minus 360k, okay. So, that is the change which comes about, right. So, because we see that what was an odd multiple of pi now has to be an even multiple of pi, right. So, consequently, we get this change, right. So, to plus or minus 360, right, times k divided by n minus m. So, once again we are going to have n minus m asymptotes. The point of intersection of the asymptotes on the real axis, that formula remains the same, okay. Sum of open loop poles minus sum of open loop zeros divided by n minus m, okay. That does not change, okay. Let us come to step 4. Step 4 remains the same because it is just a matter of figuring out potential breakaway break-in points and then determining whether they lie on the root locus, right. But then we need to be a bit careful now. Why? Because the characteristic equation can now be written as 1 minus k times A of s divided by B of s. This equation remains the same, okay, because you take the derivative for repeated roots, that condition remains the same, but then the characteristic equation is now 1 minus k A of s divided by B of s, right. So, what we need to be careful about is that although potential breakaway points and break-in points are solutions of this equation, the formula for determining the corresponding k will now become k equals B of s divided by A of s rather than minus B of s divided by A of s, okay. So, that is one change which is going to happen, okay. Why? Let me write it down here in the journal notes file, okay. So, please note that in step 4, the closed loop characteristic equation would be this, okay, now, right, with negative feedback, because that is going to be 1 minus g of s h of s equals 0. So, the condition for finding the breakaway point remains the same, okay, potential breakaway or break-in points remain the same, okay, as before, right. But once you get this, what you need to figure out is that the values of k at potential breakaway break-in points would now be determined by this formula, right, this closed loop characteristic equation. So, consequently, it will become B of s divided by A of s, right, evaluated at s equals sb, okay, rather than minus B of s divided by A of s, right, which was the case with negative feedback, okay. So, that is a change that happens here, okay. So, that is a change which one should be aware of in step number 4, but conceptually the step remains the same, right, yeah, okay. Now, step 5, does it change? Obviously it does, right, because that depends on the angle condition, the angle of departure and angle of arrival uses the angle condition. So, instead of 180 degrees, the condition becomes, like the formula becomes 0 degrees or 360 degrees, okay. Does not matter whether you put 0 degrees or plus or minus 360 degrees, it should be an even multiple of pi, okay. That is what we want there, right. So, you see that the angle of departure and angle of arrival step has changed, right, because to incorporate the change in the angle condition, right, that has come about due to the fact that we have no positive feedback, right, instead of negative feedback. So, what about step 6? Step 6 remains the same because crossover point, you substitute s equals j omega in the closed loop characteristic equation. Of course, we need to be aware that now the closed loop characteristic equation is slightly changed because it becomes 1 minus g of s h of s equals 0. So, we need to be careful with that processing, okay. But otherwise, you just substitute s equals j omega in the same equation and proceed as before, okay. You equate the real part to be 0 and imaginary part to be 0 and find potential solutions for omega and the corresponding value of k, right. So, and then like we go forward, right. So, that is the 6th step, okay. So, we see that these are the changes that are brought about due to the fact that we have positive feedback rather than negative feedback, okay. So, now let us go and repeat the exercise that we have already done, right. So, and then like we will check out what are the changes that we got, okay. So, as an example, let us repeat the same exercise and you please help me in doing this, right. So I think the first exercise that we considered was the open loop transfer function was k divided by s plus 4 times s minus 1, am I correct? Right, with k greater than 0. Was it right? Correct? Yeah. Okay. So let's do all the steps, right, in the construction of the root locus, right. So the first step remains the same. So there are 2 open loop poles, no open loop zeros. So the 2 open loop poles are at -4 and +1. There are no open loop zeros, right. So consequently, we are going to have 2 branches starting from -4 and 1 as k tends to 0, and the 2 branches of the root locus will go to infinity along asymptotes as k tends to infinity, right. So that's what is going to happen, right. So let's look at the second step. So second step is to locate the part of the real axis that lie on the root locus, right. So let's draw the S-plane and then let's figure out what happens, right. So the 2 poles were at 1 and -4. So we immediately see that the real axis is divided once again into 3 regions, -infinity to -4, -4 to +1, and 1 to infinity. So now if we take a test point here, okay, ST1, and then like look to the right, okay, how many open loop poles and open loop zeros do we have? 2, and that's even, all right. So now -infinity to -4 lies on the root locus. So now what about -4 to +1? No, right, because if you take a test point ST2 and then in this region and then look towards the right, you see that there is one real open loop pole to the right, that's odd, right. So that criteria is not satisfied, so it does not lie on the root locus. So now let's take a test point between 1 and infinity. You can immediately see that there are no real open loop poles and open loop zeros to the right. So the region 1 to infinity lies on the root locus. So immediately you can see a change, right, in the way the root locus is going to evolve, right. So consequently, what's going to happen is that one branch is going to start from -4 in this direction, okay, and the other branch is going to start from +1 in this direction. You know, in the previous instance with negative feedback, the situation was the reverse, right. The branch from -4 started towards the right, correct, and the branch from +1 started towards the left. Now the situation is just flipped, okay, and that's due to the fact that, you know, the scenario has changed, right. So that's something which we need to observe, okay. So let's go to the next step, okay. Let's go to step 3. So step 3 means, you know, like we need to figure out the asymptotes. So n minus m, that's going to be equal to 2 asymptotes, right. So what is the angle made by the asymptotes? It's going to be equal to plus or minus 360 degrees times k divided by n minus m, k being 0, 1, 2 and so on, right. So in this case you will immediately see that since n minus m is 2, I can take it as 0 and 180 degrees, right. So it becomes you substitute n minus m equals 2, you know, like you can write the solution as 0 degrees and 180 degrees, right. So those are the angle made by the asymptotes with the real axis, right. Now the question is that, like, what is the point of intersection of the asymptotes, right. So the point of intersection of the asymptotes, that formula still remains the same. So that is nothing but sum of open loop poles minus sum of open loop zeros divided by n minus m, right? What is the sum of open loop poles? It's going to be minus 4 plus 1, right, minus 3. Then there are no open loop zeros divided by n minus m, that's going to be 2. So it is still going to be minus 1.5, right? That's the same thing which we obtained previously, right, with negative feedback. So what this really means is the following, right? So let's say I have minus 1.5, the two asymptotes are just going to be along the one along the negative real axis, one going towards the positive real axis. Okay, those are the two asymptotes. Okay, that's what this calculation tells us, right? Because there are two asymptotes that are supposed to intersect at minus 1.5 and supposed to make an angle of 0 degrees and 180 degrees with the positive real axis. So obviously they have to travel along the positive real axis and negative real axis. Okay, so that's going to be the asymptotes, right? Those two are going to be the asymptotes, right? So as far as this particular root locus is concerned. Okay, now let's go to step 4. Step 4 is once again going to be breakaway break-in points. So the structure is still the same. A of s is this, B of s is going to be s plus 4 times s minus 1, A prime s is going to be 0, B prime s is going to be equal to what did we get last time? It was 2s plus 3, right? That's what we got, correct? So if we process that equation, A prime s B of s minus B prime s A of s, here prime indicates a derivative with respect to s, please remember that, right? So this implies that we will get the final simplified equation as this. So once again we get SB. Okay, I am just putting a subscript B at the end to indicate that this is a potential breakaway or break-in point. Okay, so once again we get the same solution, right, as before, what we did in negative feedback. Now there is an important difference. Okay, so as we discussed, if I want to figure out the value of k at s equals SB, now I need to do B of s divided by A of s at s equals SB. Now can you calculate and tell me what you get? Just substitute minus 1.5 in B of s, because A of s is anyway 1, right? What do you get? Minus 6.25, right? And consequently this is not okay, right? But anyway we could have figured it out, right? I did not even have calculated k, but I am teaching you a good process to follow. Okay, in this case, in this example I need not even have calculated k. Okay, but I am doing it for a general case. Okay, you give me any general open loop transfer function, how should I construct the root locus? Okay, that's what we are learning, right? Why I need not even have calculated k in this example? Because look at SB, minus 1.5. So where is minus 1.5? Minus 1.5 lies between minus 4 and plus 1. Does the region minus 4 between minus 4 and plus 1 lie on the root locus? No. From step 2 we know that minus 1.5 cannot be on the root locus. So that could have been, that is enough to show us that there is no breakaway break-in point, but still it's better. See, things will not turn out this way all the time. Okay, that's why we need to calculate k, and that's a better way to process this information, right? So you see that the value of k is negative, so consequently there are no breakaway or break-in points, right? So this implies that no breakaway break-in points for this particular case. Okay, yeah. So now let's go to step 5. What is step 5? Step 5 is angle of departure from an complex open loop pole and angle of arrival at a complex open loop 0. Does that step apply to the example? No, right. So, it still does not apply because we have only real open loop poles in this example, right. So, step 5 is not applicable, okay. So, as far as this particular transfer function is concerned, right. So, step 6 we need to figure out the crossover points, right. So, what is the closed loop characteristic equation? It is going to be 1 minus g of s h of s equals 0, okay. Please remember we are talking about positive feedback, right. So, it obviously becomes 1 minus g of s h of s equals 0. So, consequently what happens to this one? We get the closed loop characteristic equation as this. So, if we simplify this, what am I going to get? We are going to get s squared plus 3s minus k minus 4 equals 0. Am I correct? Right. Now, in this closed loop characteristic equation, you substitute s equals j omega, right. Why do we substitute s equals j omega? Because on the imaginary axis, the structure of s is of the form j omega, right, because the real part is 0, okay. That is why we are searching for whether there are solutions of this structure, right, as far as the closed loop characteristic equation is concerned. So, if you substitute s equals j omega, we immediately get minus omega square plus j times 3 omega minus k minus 4 equals 0. So, this gives us minus omega square minus k minus 4, this is the real part, plus j times 3 omega equals 0. So, we can immediately see that from the imaginary part omega is 0, right, that is the only possible solution from the imaginary part. So, this immediately implies that k should be minus 4, okay. So, this is not possible once again, right. So, because k is negative. Of course, I need not even have done these calculations once again, because step 2 immediately tells me that there is no crossover point, okay, because omega basically is 0 is not a crossover point, or s equals 0 is not a crossover point. But why should I still do this? Because I have to double check. See, step 2 only tells me that the root locus will not cross over at the origin, but I can always have crossover at some other point on the imaginary axis, right? Can I not? Right? So, in this example, it so turns out that there are no other points like that, right? But it is always better to do these steps methodically, okay. So, this means that no crossover